Hello, and thank you for joining today's presentation that will cover the Converge academic program. I'd like to introduce our two speakers for today. The first is Hannah Lystra. She is our University Relationship Specialist, which is a new role in our Madison office. She has fulfilled a need in the onboarding process for universities that are trying to acquire the academic license, and she's just under a year here as far as her time here at Convergent Science. Our next presenter will be Matthias Sulis. He started at Ignite 3D, which is a partner of Convergent Science, then became one of the first employees at Convergent Science GmbH in our Linz, Austria office. Now he is here in Madison and serves as our principal account manager. With that being said, I will now turn things over to our presenters.
Hi, thank you, Tiffany. My name is Matthias Sulis, and I'm very happy to be here today and help introducing our academic program. Let's kick off this webinar with a bit of history, our history. In the late 90s, a group of graduate students at UW-Madison established Convergent Science, that at that time was called Convergent Thinking. 2008 was our first milestone when Converge CFD software became commercially available. In the following years, we opened a few other offices in the world, and we expanded Converge's presence in other markets. In addition to the IC engine one, Converge started working with gas turbine in 2013, with after-treatment system in 2014, in pump and compressor in 2015, with oil and gas in 2019, and finally, last year with the e-mobility market. So, as you can see, after 13 years, Converge CFD software works with several applications in various industries. In terms of locations, we have now a global presence with offices in the US, Europe, and Asia. I will now pass the ball to my colleague, Hannah.
Hi, my name is Hannah Lystra, and as Tiffany mentioned, I work with university users in North and South America. In 2008, when we started selling commercial licenses, we also introduced academic licensing. At that time, leaders within Convergent Science wanted to prioritize 6 components within our academic licensing program. First, we wanted to contribute to scholarly research through publications that use Converge. Convergent Science was started by 4 graduate students. Scholarly research is at the core of how and why we started, and we want to stay connected to that community and to continue supporting academic users. We also wanted to train students in Converge before they enter industry. Especially when removing the time commitment of making every mesh by hand, students using Converge can spend significantly more time conducting research related to their studies or their career goals. Through training opportunities and online resources, we are confident that the sooner a student starts working with Converge, the more of an asset they will be to industry users. We also want to continue working with leaders in global CFD research. Academic researchers are at the forefront of multidisciplinary research. They continue to explore new areas and deepen research in existing areas, and we want to continue being a part of that work. We want to showcase academic research through Converge marketing materials. Part of the academic licensing agreement states that university users will share their research with Convergent Science. And beyond that, we want to hear from university users on their experiences and their applications with Converge. We share academic research on our social media channels like LinkedIn, Facebook, and Twitter, in our newsletter, and on our website. We wanted to expand into new application areas. Academic research is a huge way that we can branch out of our current application areas. Especially for new applications, our support and applications teams want to help and are available to help ease that process. And lastly, we want to add to our validation matrix. Because academic researchers are often looking into new areas or areas where very little research exists, their data can help demonstrate the accuracy of different features of Converge. We've stayed true to our original goals for the academic program, but with that comes a few updates that continue to benefit academic users. With academic users globally, we're striving to create easy-to-understand processes for licensing, staff in new regions to better fit the needs of schools, and more trainings held in US, European, and Indian time zones. The creation of my role means that North and South American users have a single contact person beginning with their initial inquiry about obtaining a license. That being said, our current academic priorities are, first, we want to continue contributing to scholarly research through publications that use Converge. We pay close attention to any new papers or presentations that use Converge. By offering free academic licenses, our hope is to allow students of any academic level and professors to access an industry-level CFD solver without the barriers around cost. Ideally, the earlier a student starts working with Converge, the deeper their skill and knowledge of Converge and their research topic can become. We also want to connect with academic users of Converge. Understanding the impact of academic research on the growth and development of a variety of fields, we continue to prioritize our academic licensing. A huge part of this growth is connecting with users to hear about their progress and how we can better support them moving forward. We want to continue utilizing academic research. Over the last year, Convergent Science has been creating systems to receive and share Converge research from university users. We've recently launched our first academic licensing campaign, which will provide greater impact for published pieces and simulations from academic users. We have a new academic webpage, a submission form for research simulations, and we're regularly sharing academic spotlights on our social media channels and newsletter so that the work of our academic users is seen by a larger audience. We want to refine the licensing process. For schools in North and South America, you can contact me directly to start the licensing process, ask any technical or logistical questions about the Converge academic program, or anything else that arises once you begin working with Converge. For users in other regions, the process looks very similar but is connected to a staff member in that region. Our goal for academic licensing is to present all process relevant information from the start, including primary contacts, overall steps for getting a license, and resources available to users. We also want to encourage collaborations. Several teams of Convergent Science staff members collaborate with academic users on research and written content. Additionally, we encourage collaborations between multiple universities or industry users, given that the terms of the academic licensing agreement are met, and we'll cover those details a little more extensively on a future slide. We want to continue expanding into new application areas. University research is pivotal for the growth and development of the CFD community, whether it relates to combustion, clean energy, biomedical fields, or more. As students and professors continue to come forward with new applications for Converge, we often schedule calls to work with our development and support teams to look at the capabilities of Converge that would pair well with that research. Researchers working in new application areas often work more closely with Convergent Science support and development teams so that we can ensure all Converge features are used to the best of their ability. And lastly, we want to continue working with global CFD researchers. Academic researchers continue to push the limit on current research topics and industry standards. Especially in our collaborations with university users, we like to see the goals, plans, and finalized research that students and professors take part in. Currently, we have over 360 academic users at over 65 schools in North and South America with free licenses. A few key areas that are focuses in these regions are COVID-19 research, electric vehicles, IC engines, and biomedical applications. We're continuously impressed by the research goals, programs, and rigor of academic users and the ways that they continue to develop existing application areas and create paths into new ones. Our goal is to continue growing in existing schools, to add new campuses and users, and to make the Converge academic program more beneficial for users and the greater research community. In Europe, we have over 60 schools with active licenses, and this includes over 300 users. In addition to using Converge for research purposes, several universities in Europe use Converge in classroom settings. European professors and students use Converge to study e-mobility, tunnel ventilation, hydrogen and ammonia combustion, drones, gas turbines, wind turbines, and internal combustion engines. On this slide, these are the typical steps within our licensing process. So the licensing process typically starts with either a contact us request, a Convergent Science Hub registration, or an email directly to me. Next, I'll email you and identify your role at the school, your application area, and why you want to use Converge. For students, I'll also ask which professor is involved or overseeing your work and your graduation date. For users outside North and South America, a staff member in your region will reach out for similar information. The next step is that our lawyer will send an academic software licensing agreement for the lab or department that you belong to. This is sent via DocuSign, and the professor is typically listed as the primary user, and we add students if it's a smaller team or if they'll be heavily involved in the work. DocuSign will automatically notify me once the agreement is signed, and I'll reach out to the professor and any students on the agreement to get all of the necessary licensing information. Our licenses are typically valid for 1 year, but we can send shorter licenses if that better aligns with the work. I'll send that information to our licensing team, and once I get the license file, I will pass it on to all users. And just as a note, systems administrators or IT staff are usually involved in this process as they can help install the licenses quicker. At any time during this process, you can email me if you have any questions, concerns, or if you need any additional clarity. On this slide, there are some guidelines surrounding our free academic licensing. If you are unsure if your project qualifies for free licensing or if it fits more within the paid licensing area, please reach out and we'd be more than happy to schedule a call and talk through if there's any privacy or data restrictions or anything like a non-disclosure agreement that would potentially prevent the free licensing from being valid. And even for paid academic licensing, the full commercial price typically isn't applied because they're given on a much more flexible time basis. And on this slide, there are some resources that are available to all of our academic users. The first being our hub accounts, which is what's included in the image on this screen. When you log in to your hub account, you see the folders for all available versions of Converge, TechPlot, utilities, and things like that. In the hub, you'll also find getting started guides, user manuals, example case setups, and more. Once you have a license for Converge, you'll also have access to our licensing and support teams and UDF support. It will help these processes move quickest if you email me directly, and I can connect you with the best team or staff member at Convergent Science. As an academic user, you also have access to Zoom-based training sessions, which are updated monthly and cover a variety of topics. And those are free in Europe, India, North and South America. Under the training page on our website, you can also sign up for free personalized case setups. And if you're interested in any kind of high performance computing, one option that is available is through Rescale. Rescale is a cloud simulation platform that helps engineers and scientists build, compute, analyze, and scale simulations with high performance computing. You can run your simulations at Rescale without the cost of Converge, though you do still have to pay for the Rescale use. If you're interested in using Rescale for your work, connect with us and we can talk more about what that process looks like.
Thank you, Anna. Let me start talking now about our training program. We offer a wide range of sessions for all experience level and focus on several applications. There are what we call intro session for new Converge users and advanced session for those who attended already the intro session or for those with more experience with Converge. All these sessions dive into specific topics like FSI, compressor and pump, after treatment system, etc. Please remember that you don't need to be an active user to attend the session. In regards of paper collaboration, we have a long history of partnership with universities across the world. If you and your research group are interested in developing a topic using Converge, we will be thrilled to work with you on that and to offer all the technical support you need. On our website, you can find a selected bibliography with over 900 papers that are a testimony of our work with research groups, universities, and companies. UDF stands for User Defined Function. We offer a 2-hour training session on this topic, and I won't try to compress that in a minute here. What I would like to share today is that this advanced capability in Converge allow a user to implement a model that is not currently available, for example, a new spray or combustion model. Our support team is ready and available to help implementing any UDF and to share all the internal resources available to make the process as efficient and as easy as possible. In addition to the help from our support engineers, you can download the Converge UDF manual from our hub. They give you all the details on this topic. Thank you.
Now I'd like to highlight some current work from a few of our university users, the first being at Clemson University. Benjamin Lawler is an associate professor in the Automotive Engineering Department at Clemson University's International Center for Automotive Research, CU-ICAR. His research is related to improving the efficiency and emissions characteristics of internal combustion engines, including a focus on advanced low-temperature combustion strategies including HCCI, RCCI, TSCI, and others. Dr. Lawler's research also focuses on the use of alternative and sustainable fuels such as alcohols, biodiesel, natural gas, and hydrogen as a potential pathway toward a net carbon neutral transportation solution for future engine-powered vehicles. Additionally, Dr. Lawler has prior experience with alternative engine designs and drive cycle modeling and simulation of various vehicle architectures, including hybrid electric vehicle configurations. Prior to joining CU-ICAR in August of 2019, Dr. Lawler was an assistant professor in mechanical engineering at Stony Brook University from 2015 to 2019 and a postdoctoral researcher at Oak Ridge National Laboratory from 2013 to 2014. He received his doctoral and master's degrees in mechanical engineering from the University of Michigan and his bachelor's degree in mechanical engineering from the University of Massachusetts Amherst.
Thank you for your attention attending this Convergent Science webinar. My name is Ben Lawler. I'm an associate professor at CU-ICAR, and today I'm going to talk to you about how we use Converge CFD software at CU-ICAR. We have these active projects, and that's what I'll share individual slides about with you, starting with a collaboration with Sandia National Labs using large eddy simulations of advanced compression ignition combustion. Specifically, we're looking at partial fuel stratification, and we're helping to provide feedback related to a gasoline surrogate composition and mechanism, and using large eddy simulation to provide feedback about air-fuel mixing. We also have a Department of Energy funded project with Acades Power, and I'll tell you more about that. And finally, we developed a novel co-simulation for studying thermal barrier coatings using CFD and FEA. And we have two active projects related to that. One is an SBIR project, and the other is an Aramco Research Center funded project on gasoline compression ignition with TDCs. Finally, we have a new Army center at Clemson called Virtual Prototyping for Ground Systems, Viper GS, and I'll tell you about how we're using Converge in that new Army center. So starting with our collaboration with Sandia National Labs, we're taking a CFD model of their medium-duty ACI engine, and we're simulating it in Converge with LES simulations to provide feedback on the in-cylinder air-fuel mixing and the impact on combustion and emissions. One way in which we do that is with this joint PDF shown here, and you can see the temperature distribution along the bottom and the equivalence ratio distribution along the left. The heat release is shown along the top, and the red bar is at what point in the combustion process the joint PDF is currently at. You can see just after injection, we have this coupling between equivalence ratio and temperature, where the cooler regions are richer from that evaporative cooling of the fuel. What's also interesting at this low load case is that all of the regions ignite around the same time, which is distinct from high load PFS, where the richest regions would ignite first. So these are some of the insights that we can generate with these joint PDFs and provide feedback about the combustion process in PFS. Additionally, we've tested a couple of different surrogate compositions for them, and this is still ongoing. We're testing more to try to provide feedback about the best possible surrogate composition to match real-world gasoline, which is very hard to do, but it is critical to accurately capturing PFS combustion. The next project that we have is this Acades Power project funded by the Department of Energy Vehicle Technologies Office. We're helping Acades to take their 3-cylinder engine and make a family of engines where there would be a 2-cylinder or 4-cylinder variant, depending on the application, that shares common parts. So what we're specifically doing with CFD is we're modeling the entire multi-cylinder engine with intake and exhaust systems. We're helping provide feedback about the breathing, the port opening timings, and the air system configuration that would be required for the different engine variants. The reason this is challenging is because it's a very large computational domain, and we have to simulate over a number of consecutive cycles to remove the impact of initial conditions. So far, we've found that Converge 3.0 is crucial to getting the turnaround time down because of that better load balancing and parallelization with 3.0 compared to previous versions of the code. And this table just shows that we're able to get good agreement between the CFD and the experiment in terms of the breathing characteristics. The next topic is this co-simulation methodology that we developed for studying thermal barrier coatings. What we do here is we take CFD simulations and we take the surface heat fluxes and prescribe them as boundary conditions into FEA. Within FEA, we then solve for the surface temperature and prescribe that back into CFD, varying both spatially and in time. And we iterate on this process until we reach a steady state. Converge does have conjugate heat transfer, and conjugate heat transfer works great for a lot of applications. We have used it in the past. But we found that this iterative method is maybe better suited for thin thermal barrier coatings so that we can get better control over the grid within FEA and within CFD. And we can learn through that iterative process what are the impacts on FEA and CFD from the grid. And so what we're showing down here is just an example result from that FEA simulation where we solve for the surface temperature on a piston due to combustion. And so finally, on this last slide, we have our new Army Center is virtual prototyping for ground systems, Viper GS. This is being currently stood up, and it's funded by the Department of Defense, involving more than 60 faculty members at Clemson. There are three main focus areas. One is related to autonomy, and one is related to the virtual prototyping. But what's also critical is the propulsion and smart energy systems for these vehicles of varying scale. So this graphic on the far right is just to show that the propulsion system used in each of these vehicles will be different. And we would like to develop modeling and simulation capabilities to help provide feedback to the Army about the optimal propulsion system for each of these vehicle applications. So specifically, we're using CFD engine models to better understand heat transfer and combustion in 2- and 4-stroke military engines. So with that, I'll thank you for your attention. I would like to acknowledge the funding for these projects. And I would also like to acknowledge our collaborators at Sandia National Labs, Dr. John Deck and Dr. Dario Lopez-Pintor. And finally, special thanks to the PhD students who provided most of the content, specifically Patrick O'Donnell, but also Sean Ari and Rahul. If you have any questions or would like to discuss more about any of these projects, please feel free to contact me at this email address. Thank you so much for your time and attention.
Next, we'll hear from Dr. Alejandro Roldan Alzate, who is a professor at the University of Wisconsin-Madison. Dr. Alejandro Roldan Alzate received a PhD in mechanical engineering from the University of Wisconsin-Madison in 2008. He then joined the Vascular Tissue Biomechanics Laboratory at the same institution as a research associate. In 2010, Dr. Roldan Alzate joined the Department of Radiology at the University of Wisconsin-Madison as a cardiovascular modeling scientist, and in 2015, he obtained a joint faculty appointment in the Department of Mechanical Engineering and the Department of Radiology. Dr. Roldan Alzate's research focuses on fluid dynamics analysis of physiological and pathological flows using a combination of medical imaging, additive machinery, additive manufacturing, particle image velocimetry, and computational fluid dynamics.
Hello, everybody, and thank you for attending this presentation. Today, I'm going to be talking about the collaboration that we have established between Converge and the Cardiovascular Fluid Dynamics Lab at the University of Wisconsin-Madison. We've been working on numerical simulation of physiological flows based on patient-specific images. We started by trying to understand how could we get Converge software to help us in the process of understanding physiological flows. And one of the main applications for computational fluid dynamics in the market is mechanical heart valves. For that reason, we started with a simplified version of it, and we found how the adaptive mesh refinement methods that have been developed by Converge are really well suited for what we want here, which is moving boundaries and complex flows. One of the things we did was we started analyzing, okay, how can we test the comparison of Converge software with other softwares, and we started trying to play with the settings of the adaptive mesh refinement. And this was just a preliminary study. However, we found that if we wanted to keep going with this, we needed to kind of standardize the way in which we simulate our problems. For that reason, we joined forces and we recently published a paper on adaptive mesh refinement for the FDA nozzle computational fluid dynamics efficiency, which is a standard that the FDA came up with to test computational softwares that are to be applied in the medical field. For this, we used the nozzle geometry that you can see in the slide, and we compared the data to previously obtained experimental results with particle image velocimetry. So this gave us some thoughts about, okay, now that we have validated or we have standardized the way in which we do this, we can go into more patient-specific analysis. And for that reason, we started looking at aortic coarctation, which is a disease that kids are born with, in which the aorta, which is a blood vessel coming out of the heart, is narrower than normal and imposes some complex flows. So what we did was, okay, MRI, for some reason, misses some of the information. So if we can use computational fluid dynamics to understand the flow in the aneurysm and other regions, then we are enhancing what MRI can provide us with for clinical purposes. Same thing happens in cases where there is a stent, for example. In this case, there is a stent in this region where you don't see signal, and this is MRI data. And what we do is we generate the geometry and we get the data that was missing from the stent. So just so to give a brief background, stents are made out of metal, and that metal imposes an artifact in the MRI signal that doesn't allow the velocity measurements to show up. So with computational fluid dynamics, we're able to fill the gaps between what is existing and what is not from MRI. Continuing with the same analysis, we just tried to compare how 40 flow MRI, which is what we normally use clinically, can be enhanced with CFD, and then think about how in the future we could use this for clinical diagnosis and surgical planning. Connected to this, we started thinking, how can we use computational modeling to clean the MRI data and enhance the MRI data? So for that reason, we mixed machine learning and computational fluid dynamics by generating a number of simulations with patient-specific flow curves and different anatomies of brain aneurysms to clean the MRI data. In that way, we just convert the data to get something that is divergent-free and that allows us to say, we are putting physics into the reconstruction of the MRI data, and we're not just getting some crazy vectors that are not making sense, which is something that could happen with MRI. So what we do is we just get a convolution neural network to just train the MRI data to look more physically realistic. And as you can see here, the noise of the MRI data can be cleaned really well with the data from the train network with the CFD simulations that we perform with the CONVERGE software. This is even a more clear and easier to understand way of looking at it, because you see noise everywhere, which means there is non-physical motion that the MRI is capturing, whereas the CFD allows us to just clean it up and say, those regions were not supposed to have flow, those regions were supposed to be zero velocities. And in that way, any calculation of any derived parameter like Walsh stress or pressures or velocities would be more realistic. For example, here is the normal 40 flow data, here, or the MRI data, and here is how it is after cleaning with CFD. Velocities at the wall are more realistic, close to zero, and it allows us to go with realistic physics. Recently, we have implemented this method to do urinary dynamics, which is used for patients with enlarged prostate or problems with their bladder. The reason for this is there's not non-invasive way of assessing this, and we just implemented some realistic MRI data, couple it with computational modeling, and we're able to analyze how the vorticity in the bladder is affected by the prostate enlargement and other problems. And with this, I mean, what we can say is computational fluid dynamics is not currently used clinically unless there's a few companies out there that can use medical imaging to detect coronary blood flow. It has high user input time and high simulation to runtime. It is not used for medical device regulation, which is something that with those standards from the FDA, that's the field that this would go to. Mainly because there is uncertainty and there is some other factors that could affect this. But we think that solution adaptive refinement can minimize these factors and can help us get into a more, to be able to use computational fluid dynamics more actively in the clinics. With this, I'd like to thank you and I'll welcome questions.
Next, we will have a Converge Studio tutorial done by David Rowinski. David Rowinski earned a PhD in mechanical engineering from Cornell University in 2013. In 2015, he joined Convergent Science to work on IC engines. Today, David supports new applications for Converge.
We'll now be demonstrating Converge's ease of use by performing a complete case setup on an example case. The case we've chosen for this demonstration is a quadcopter fluid structure interaction problem in which the speed of the 4 propellers is prescribed with profiles. The motion of the copter is then determined through fluid structure interaction. This particular case setup is selected to showcase how easy it is to include extremely complex motion and geometry of parts in a CFD simulation. We'll get started by launching Converge Studio and importing an STL formatted geometry. The STL file is read in, and after that, can choose our STL format, quadcopter geometry. The STL file is read in, and now we'll inspect the imported geometry. Let's draw a clip plane across the center so we can take a closer look at our geometry. Let's zoom in there around the quadcopter. See, we have our outer domain. Then we'll change that clip plane so we can see the full drone. And after that, we'll begin the process of boundary flagging, where we group parts of our imported geometry into boundary conditions. Start by creating 7 boundaries, and we'll first flag the ground. We'll label that as the ground. Then we'll zoom out and select that far field boundary, which we'll rename as far field. We can hide those 2 boundaries now so that we can focus in on our quadcopter, and we'll be careful to make sure to keep the same orientation and numbering consistent with our case setup guide. Let's flag the 4 propellers by surface there, propeller 1, 2, 3, and 4. Then after that, give the boundaries the appropriate names. So we've got propeller 1, 2, 3, and 4. And then our last boundary to select is our drone frame. So we'll select that and give that an appropriate name. Now you can see all our boundaries are assigned. We can take a close look at our quadcopter with boundaries flagged. Now we'll begin our case setup, and we'll choose our material type to be a gas phase. We'll add some body forces for gravity. And under our physical models, allow turbulence and fluid structure interaction, as well as adaptive mesh refinement and fixed embedding for our grid. Start with an ideal gas formulation for our gas properties and set our turbulent transport properties to our defaults. Then we'll add under our species air, which is a mixture of gases. So we'll create what we call a composite species, which is a mixture of fixed proportions of the species. So we'll add the oxygen, and we'll add after that the nitrogen to our air, and then we'll set the mass fraction of each of those components. Now that we have this mixture defined, we can add it to our simulation under our available gases. For our run parameters, we'll mainly choose our defaults for transient compressible flow with energy and momentum solved for. And under our time parameters, we'll choose our start time and our end time. We'll use dynamic time stepping. So we'll have our CFL numbers to determine our time step, as well as some min and max limitations. After that, let's define our body forces. We have gravity, in this case, acting in the negative z direction. For our solver parameters, we'll leave everything at the default recommendations of Converge Studio. Our next step is define regions, and we'll set up our main region to be atmospheric air. After that, we'll define all of our boundary conditions. So the ground will make a wall with our standard law of the wall type of boundary conditions and fixed temperatures. Our far field will be an inflow set with a hydrostatic pressure with a reference point and a reference pressure. The incoming fluid, if there's any entrained, will be air. After that, we'll go through and define the rotating conditions for our 4 propellers. We'll set those to be rotating, moving, so that the geometry actually moves, and then we'll need to define the rotation axes. So in this case, we'll pull our origin, which is our XYZ coordinates, from our case setup worksheet, and we'll simply paste those values in. Our rotation axis for this first propeller will be about the negative z direction. Well then, after we've got this one defined, copy over this setup to the other 3 propellers, and then after we copy them, we'll adjust their rotation centers. So let's go to propeller 2, copy that rotation origin from the worksheet, and then we'll paste that into the case setup. Make sure the direction is appropriate. Then we'll do the same thing with propeller 3, where we copy that rotation origin and paste that as the rotation center. And similarly with propeller 4, we'll copy that rotation origin and paste that. Now for propellers 3 and 4, we also have to change the direction since these ones rotate in opposite directions compared to propellers 1 and 2. For the drone frame, before we go to the drone frame, we also need to define our profile. So we have set our velocity profiles so that we have a rotation rate that changes with time to allow the quadcopter to perform some maneuvers. So we'll paste a table with rotation angle versus time profile so that for each of these propellers, we can individually control the speed versus time. We'll paste that for propeller 1, and then for propeller 2, we'll make a similar file, which will contain profiles that are slightly different from propeller 1 to allow the maneuvers to be performed during the simulation. We'll paste those rows in, make sure it has a unique name, and then go on to propeller 3. For propeller 3, we'll choose a similar profile from that worksheet, copy that, and paste it in, just like before, giving that profile its own name. And then after that, we'll go to our last propeller, give that one, we'll adjust that name in a bit, copy those angles versus time, and then paste those into our profile. And then let's be sure to give that one a unique name. We'll call this prop 4 speed. Type that in, hit accept. Now our propellers 1 through 4 should have a unique rotation center and a speed versus time profile to match our maneuver. For the drone frame, we'll assign that to the same region and set this one up to be part of the FSI object, which we'll define in a bit. Use our standard law of the wall boundary conditions, and this boundary will be all ready to go. So now we have all of our boundary conditions defined. We have an issue that we haven't defined our FSI object, but don't worry, we'll get to that soon. So Converge has a rich set of turbulence models available, including RANDs, DES, and LES. In this case, we'll be choosing one of our standard RAND models. For our fluid structure interaction setup, it's quite simple from the user's point of view. We'll simply add a rigid FSI object, which we'll call the drone, and then we'll add all of the boundaries which make up that FSI object. This is going to include the frame as well as the 4 propellers. Even though those propellers have individual motion profiles, they'll be moving together with our FSI object. Now we'll define the properties for our FSI object, including the center of mass, which in this case will define that from our setup worksheet where this center of mass was pre-computed. We'll copy over that center of mass in, and then for our mass, we'll use a constant mass of the 0.2 kilograms. So we'll assign that. For all the constraints, we'll leave those as our defaults. So our rigid FSI object is going to move in all 6 degrees of freedom. Now that our FSI object setup is complete, our boundary setup is ready to go. We'll move on to the grid. With the grid, we'll first define our base grid, which is our biggest grid cells. In this case, we'll use a base mesh size of 0.1 meter, since this is a pretty large geometry. So we'll set that to be 0.1 for X, Y, and Z. And then we'll move on to the AMR setup. For our AMR setup, we're going to define our maximum number of cells. In this case, we can use 1 or 2 million. We'll set that to be 2 million just for demonstration. Then we'll assign our region where the AMR will be active. We'll want to refine around the regions of high velocity gradient. So we'll set our SGS value for velocity. Next, we'll move on to boundary embedding so we can have some finer grid around the propellers. We'll define a scale of 6 in this case, and 3 layers. Then we'll copy that to the other 4 propellers and assign propellers 2, propeller 3, and propeller 4 to have the same type of boundary embedding. Lastly, we'll add another embedding right on the drone frame of a little bit less scale than what we have on the propellers. So our grid setup is all complete, and that grid will be generated autonomously during the simulation. Next, we'll choose our post variables, the variables that we'll be able to look at as the simulation is running. We'll choose vorticity, Y+, as well as the Q criteria, as well as our standard outputs. And then we'll define a couple other output parameters, including the intervals at which our output files are written, including the 3D output, our text output, and our restarting output. Now our case setup is all complete. You can see those green check marks. We'll save our case, export onto our HPC environment folders, select our run directory, and export all of those input files there. We'll be ready to launch our job on our workstation. So after that, we can move to our run directory, begin the solver, and see our output that the input files have been read. The grid has been created at runtime. You can see those different levels. And now it's going to begin solving all of our equations. You can take a look at the output to see the time step growing. And we'll let that simulation run as it progresses. As the simulation goes, we can move on to Converge's post-processing module. First, the line plotting, where in this case, we'll jump to a directory that has been pre-run, a very similar case setup. So we'll skip over to that output directory where we'll be greeted with a list of the files created during the runtime. Let's first load up the cell count file. We can see that cell count growing from about 100,000 cells to 1 million, which we capped for this run. Then we'll look at the drone motion. You can see for the X, it started that maneuver at 0.4. So if we look at our motion profiles, that maneuver to move in the X direction started around 0.4. The Y maneuver began a little bit earlier, and we can see that taking off about 0.1 seconds. But the main component is our lift, going up to about 3 meters steadily throughout the simulation. Of all these line plotting things, we can also look at an output of the quadcopter's motion produced through TechPlot for Converge, where we can look at a cut plane showing the grid and how that's automatically refined following the motion of that drone, as well as an ISO surface on velocity. Thank you very much for your attention and seeing what Converge can do for this simulation.
Thank you, David. That was a great video. It always amazes me how easy it is to set up a case with complex and moving geometry thanks to our automatic grid generation. Now, let's touch base on our newest version, Converge 3.1. We added several new models and features, and I'm going to give you some examples here. Multi-stream. Converge has several different types of solvers to handle compressible flow, incompressible flow, heat transfer, and more. In Converge 3.1, each independent portion of the domain or stream gets its own set of inputs. This allows complete flexibility for multi-physics problems by allowing any solver combination in the same simulation. Discrete Parcel. In Converge 3.1, the user is able to define as many different parcel types as they want, with its own prescribed behavior. In version 3.1, parcels are not just limited to liquid, but can also be solid. VOF. Converge has had VOF capabilities for some time, but in Converge 3.1, updates including flux-corrected transport have been added. The flux-corrected transport model now allows predicting the separation of phases after they have been mixed. Steady solver. Converge was originally written to be a transient CFD code, with steady-state capabilities being added later. In Converge 3.1, several steady-state improvements have been added, which continue to make it faster and more stable. Hannah, to you now.
Our 2021 Global User Conference will be held online and will feature a variety of presentations from speakers across the globe. Registration opens June 1st, and the link will be available on our website. You can also find it in our newsletter, and there will also be updates on our social media in the time leading up to the user conference. Over the next several months, topics and details surrounding the keynote speakers will be announced. As academic users, you also have the ability to submit an abstract. And on this page, you will see a list of the current contacts for the regions that we work in right now. If you're outside of these regions, please fill out a contact us request on our website, and we will get you in touch with the best region or the best staff member to help support you in getting a license or answering any questions that you might have regarding our academic licensing. And these email addresses and this information will be shared with you after the webinar is completed. So those will be available to you moving forward. Thank you for joining us today. If you have any further questions about Converge academic licensing or are interested in getting a license, again, the emails from the previous screen will be shared once the webinar is complete. And there is also still time to register for our introductory and advanced trainings in June. The link for our US and European-based trainings will also be included in the post-webinar email. You do not need a licensing agreement in place or an active license to attend training and work hands-on with Converge, so that really is a great resource to get a little more familiar with the software.
Okay, so one question that we do have, Hannah or Mattia, either of you can take this, but someone's asked, can the license be used for academic project which has an industrial partner?
Yeah, so this is a great question, and this hits a little bit on the slide that covered the guidelines for free academic licensing. We do, obviously, from the presentations from Clemson and the University of Wisconsin-Madison, we do have several universities that work with industry users, and the biggest note with the free licensing, if it's with an industry user, is that there can't be any data restrictions. So what that looks like is you realistically have to be able to share your models and input files with us. We don't always ask for it, but if there would be a support request or something similar, the free license means that you'll share that with us. But again, if you have any questions, we can schedule a phone call and kind of talk through the project and what the industry use is going to look like.
Just to follow up on that question, should you contact the European representative, seeing as you are in the UK? Yes. We do have offices throughout the globe, and it's best for you to contact the office that supports your area. So definitely. And it looks like we don't have any additional new questions. Again, we encourage you guys to visit our events page for upcoming events, whether it's training or conferences that we will be attending virtually or face-to-face. And again, if you have any questions pertaining to a case, definitely reach out to support. We look forward to presenting more material to you as the year goes on. And again, stay safe, and we'll speak again soon. Thank you. Bye-bye.